There is an exercise that I invite you to do. Derive the second moment of inertia of those two very common shapes that would occur in the engineering applications about an axis passing through its centroid. So of course, obviously, the centroid of the rectangle is located here. Similarly, for this one, for the circle, the centroid is here. For this axis passing through its centroid, what is the second moment of inertia of them? Well, to do this, it is easy. So for about this axis, well, it is horizontal, so I just treat something as y. So I equals to the double integral of the entire area y dA. Oh, sorry, it should be y squared because it is the second moment of inertia. Okay, so don't mix them up. Then, for this moment of inertia, how to evaluate? So we know that since it is talking about the vertical direction, treat y equals to 0 for this axis, then the upper limit will become y equals to w over 2, lower limit is minus w over 2. So the integral will become for x with length L and the width with the upper and lower limit to be w over 2 and a minus w over 2 of y squared dy dx. So it is significant that it should be, so you know that for the inner integral, after you evaluate, it will become the constant. So the integral will become the integral of dx over the length L, which is significantly to be L, times, or I don't write it like this, times the integral from w over 2, from minus w over 2 to w over 2, okay, y squared dy. The result will become w cubed L over 12. Notice that it is a very common result that you have to know, because after you dealing with this, dealing with such a common shape, you know, okay, for this common shape, there is a formula describing its second moment of inertia, right? So you don't need to use the double integral technique again and again to find the moment of inertia. Instead, you use the equation directly. Next, let's try to evaluate the moment of inertia of a circular shape. So we know that the moment of inertia equals to the double integral of the entire area of y squared for every differential area element. It equals to, so we know that the lower limit for the theta would be 0 and upper would be 2 pi. And for r, significantly, it is from 0 to r. But what is y? We know that y equals to r sine theta. Then you can write r squared sine squared theta because it is y squared, okay? And dA equals to r dr d theta. The integral would become 0 to 2 pi, 0 to r cubed sine square theta, dr d theta. It would become r to the power 4 divided by 4, 0 to 2 pi sine square theta, d theta. And we know that sine squared theta equals to 1 minus cosine 2 theta divided by 2. Therefore, it will become, so we take out the divide by 2 first, then the outside will become r to the power 4 divided by 8. The inner world will become 1 minus cosine 2 theta d theta. But we know that even though I integrate this up, it will be 0 because the lower end limits are 0 and 2 pi, which means that the integral of cosine 2 theta with this lower and upper limits will be 0. Therefore, this piece becomes 0, and consequently, we conclude that it is equal to r to the power 4 divided by 8 times 2 pi equals to pi r to the power 4 divided by 4. It is similar to the rectangle example. It is also an important result that worth you to remember, or sometimes it can be provided by the formula sheet of the course, but I'm not sure whether it will be provided though. So, but for this video, I have to emphasize that we are just going to illustrate you how to apply the mathematics skills to our physics applications. So I don't think for this course the math will become too difficult to do.